So in this podcast, we're going to talk about entropy, which is, as we'll see, measures how much disorder there is in a system. So the definition of entropy is the measure of the disorder or the randomness in a system. And just like enthalpy, we don't really care about entropy, which has the symbol S, by the way. We care about the change in entropy. So if it's increasing entropy or increasing disorder, it's going to be a positive delta S. And that happens if you increase the number of particles or increase the number of moles of a gas, because gas is so much more disordered than a solid or a liquid. So for example, we have this example, this reaction, nitrogen plus hydrogen gives us ammonia. So if we count up moles of a gas on both sides of our equation, on the left we've got 1 nitrogen plus 3 hydrogens, 4 moles of a gas. And then on the right we have 2 moles of ammonia, so 2 moles of a gas. So it goes from 4 to 2, so there is a decrease in entropy S, and that's going to be a negative entropy change. So it goes from greater entropy to less energy, which actually is, not a usual process, so there must be other stuff going on with energy and bonds and things like that. So predicting the sign of delta S, look at each equation. So in the case of number 1, going from 1 mole of a solid to a solid plus a gas, that's going to be a positive entropy change. If we go from 2 moles of a gas to 1 mole of a gas, that's going to be a negative entropy change. So work these and then check your work. Solid dissolving in water and making an aqueous solution, that's going to make more particles, so it's a positive entropy change. 2 moles of hydrogen plus 1 mole of oxygen gives us liquid water, which is much less disordered, so that would be negative. On the other hand, if we have liquid water and we vaporize it and turn it into a gas, that's going to be a positive entropy change. So in pictures, for number 6, we've got a substance that's a solid vaporizing to a gas, so that would be sublimation, definitely a positive entropy change. And in this reaction, we have more gas particles combining to form a product that has fewer gas particles, so that would be a negative entropy change. We can also do the math associated with entropy, calculate delta S, very similar to what we did for delta H. Again, we are going to use entropy values, standard entropy values, which are found on the data chart in the back of your packet. You are given these numbers. You don't have to remember any of them. And because entropy is a state function, like enthalpy, it doesn't matter how we get there. So we can use an equation that's very similar. It's similar to Hess's law, but it's not Hess's law because it's entropy. But the change in entropy is going to be the sum of the entropy of the products minus the sum of the entropy of the reactants. And we can actually measure the entropy associated with every formula, and those are found in the chart, in the thermodynamic charts. And the one thing that we need to notice about entropy is the numbers are smaller, the numbers are typically in joules instead of kilojoules. So later on when we have to combine them, we have to think about the units. And the chart is labeled with joules. So for these reactions, look up the entropy values, find them on the chart. That can take a while. H2S, SO3, sulfur S. If you're given more than one choice, for in the case of sulfur, it can come in more than one form. Use the first one. which in this case is 31, and then water. Be sure to make sure that check the state of water, because water in the gas form has a different entropy than water in the liquid form or the solid form. So be really careful with states. The numbers here I wrote above just to keep track of them. And then plugging into the entropy equation, the delta S, which is what we're looking for, is the sum of all the entropy of the reactants. So the reactants are sulfur and water. Those come first. Multiply them by the coefficients in the balanced equation. So it's going to be sulfur times 3 plus water times 2. All of that is going to be added together. Pay attention to signs. And then subtract it from the sum of all the reactants. So again, H2S is going to be times 2. SO3, there's only one of them. So it's not going to be multiplied by a factor. And then plug that all in, and then you're going to calculate the change in S. And in this case, it's positive 5.2, which is a really small number, so it's very close to 0. So this one was really hard to calculate. My prediction, hard to predict. I put a plus and minus because I was actually unable to predict this, because in this case we have 3 gas particles going to make 3 solid particles plus 2 gas particles. So there's a decrease in gas, but there's an increase in particles, so I found it hard to predict, which is probably why the number is so small here. So for the rest of these, go through and do the calculations, and then turn it back on and check your work. Okay, so seeing how they stack up to the predictions, my predictions were over here, looking at the equations, and then the actual math is worked out here. So positive change in entropy, which does make sense because we have 2 moles of a gas going to form 3 moles of a gas. So there's an increase in gas particles, so that definitely would be an increase in entropy. For number 3, we've got solid plus 2 moles of a gas, making a solid plus 3 moles of a gas. So again, increase in entropy. For dissolving HCl gas, I was unable to predict because gas particles have a lot of entropy, but so do aqueous solutions, and I wasn't sure how that would compare. And it turns out that it is a negative entropy change, so it is a decrease in entropy. So gas particles have more entropy than aqueous solutions. And then for the last one, positive change, 2 moles plus 3, 5 moles of a gas, going to make 2 moles plus 4, going to make 6, increase in entropy. And again, that fits what we see with the calculations, which is positive 91.2.